Hello everyone. In today's video, we're going to derive the famous Kutta-Joukowsky lift theorem, and we're going to do so starting from this equation at the top from vortical impulse theory. This is one I derived in a video previous to this, under the specific assumptions that we have an unbounded fluid domain where the fluid is incompressible. This specific version is for two-dimensional flows, and we have assumed that there's no vorticity outside of V infinity. So any vorticity that's been generated has to have been kept inside. And just to show the goal that we're aiming at, so if we have an airfoil embedded in an unbounded domain, and it's fixed at a fixed angle of attack, it's not moving, we get a lift, which the Kutta-Joukowsky theorem gives us as density rho times u infinity, being the incoming velocity, which is assumed to be steady and constant, times by the bound circulation. So here is the incoming free stream velocity. I've shown the lift there, which is perpendicular, and we have some bound circulation, gamma b. Now looking back to the equation at the top of the page, this second term, we're actually not going to have to deal with this in this particular case. So looking at SB, we've got a variable, the velocity u on SB. We can invoke the no slip condition, by which u is 0 everywhere on SB because SB is not moving. And so this second integral is not going to contribute in our derivation. And we're left only with this time derivative of impulse. And to proceed, I'm going to divide up the domain V infinity into two. So firstly, I have V1, which is a volume surrounding the airfoil, but not including the full fluid domain. And we are going to define this such that the flow inside V1 is steady. And then any unsteadiness that's occurring has to happen in the remainder of V infinity, which I'll call V2. And of course, our original V infinity just equals V1 plus V2. Now, it's worth noting that in most classical derivations of the Kutta-Joukowsky lift theorem, we're looking at an unbounded domain in which the starting vortex that's generated by the airfoil when it took on its angle of attack has convected outside of the domain. But because this equation we're using assumes that no vorticity has yet left V infinity, it must still be inside V2 and convecting, such that the flow is not steady in V2, but rather we have some starting vortex, which is convecting downstream at a velocity, which I'm going to call ucv for the convection of the vortex, and we have gamma v being its strength. Now, by Kelvin circulation theorem, we expect the total vorticity inside of V infinity to be 0, so the circulation around the airfoil and the starting vortex have to be equal and opposite, so this is just negative gamma b. And if the vortex is sufficiently far away from the airfoil so that the airfoil is not influencing its motion, then we would expect this convection velocity to just be the free stream velocity. So now to proceed, I'm going to go back to the original equation, and I want to take this impulse integral and split it up into two over V1 and V2. So we'll just rewrite that out down here. So we have the changing impulse in the two subdomains. Now we've defined the first domain on purpose such that the flow is steady, which means that the time derivative of all parameters inside of it is 0. So this term vanishes. And to proceed further, what I want to do now is to move this time derivative on the second term inside of the integral. Now, in order to do that in a useful way, we're going to need to express this in terms of a material volume. So a static volume is something we just defined as this region of space. Now I want to look at a material control volume where, as it evolves in time, it is following a specific group of matter, a specific block of fluid. So its boundary in this case cannot be fixed in time. Okay, so here we have this pink boundary that I've defined enclosing the starting vortex and moving with it. I will call that volume Vm for material, and the surface bounding it is Sm. Now, one other assumption I'm going to have to make is that this vortex is actually axisymmetric. So let me redraw it. There, I've redrawn it as axisymmetric as I can. Now, I've purposely drawn this such that there is no vorticity in V2 outside of Vm. That is, on the domain V2 minus Vm, omega vorticity is equal to 0. So with that, this term here, this becomes the time derivative of the integral over the material volume, and now I have no problem moving this time derivative operator inside. When I do that, I get this integral here minus this integral here. So now that we're looking at material volumes and we're looking at material derivatives, so I've used the capital D, capital DT notation, which is often used to denote the material derivative at a point. So instead of looking at the changing parameter, such as vorticity or velocity at a point, I'm now considering the changing parameter of a specific fluid element, which we are in some sense following. So with that in mind, this dx dt, the changing position of a fluid element, is by definition just its velocity. And over here, the material derivative of vorticity, we can consider that through the vorticity transport equation. So let me write out the vorticity transport equation down here. So here it is here in the form, the most commonly used form. The first term here is an unsteady term. The second is vortex convection. The third is tilting and stretching. And the last is diffusion. Now, because we're looking at 2D flows, there is no such thing as tilting and stretching in 2 dimensions, so that term goes away. And we're actually going to combine these first two, because in this form we're looking at what's called a Eulerian frame of reference, or a Eulerian description of the flow. So this partial omega partial t is referring to the changing vorticity at a specific point in space. But recall, we're looking for the changing vorticity of a fluid element. So if we combine the unsteady and the convection terms, we have the material derivative that we're looking for. So let's look back up here. We have now, we can substitute this into the second pink integral here. So let's rewrite out what we have now. So scroll back down. And we have these two integrals here. So we have one involving u cross omega, which is often referred to as the Lamb vector, or simply the vector force. And we have this second term that involves diffusion. So we have two processes being described here. What we're looking at is the changing impulse in V2, and that impulse is changing due to convection and possibly here diffusion. Although we will now show, under some special assumptions, how this second term is going to vanish. So I'm going to relate this volume integral now to an integral over the bounding surface of Vm. So we have this relation here. Now I'm not going to prove this for the sake of time, and I will note that I have actually moved the kinematic viscosity nu outside of the integral, assuming it to be constant. So this is for a Newtonian fluid. And since I've given this as an identity without proof, let me give you a reference. And I'll give the full reference in the description below the video. Now, going back up to our sketch, we've drawn this intentionally as though the vorticity is away from the boundaries of Sm, so we're free to define whichever material volume we want. So we're defining one that's sufficiently large that the vortex is contained inside of it, and we are assuming that there is no vorticity crossing that boundary. So that means in our equation down here that omega is 0 on Sm, as well as the gradients. So there's no normal gradient of vorticity either. We're sufficiently far away that both of these go to 0. So now we're left only in this force equation with this lam vector term. So now to continue, it will be convenient to define the velocity such that it is the sum of the free stream velocity plus some disturbance velocity, which we'll call u prime. Or perhaps it's better to describe it as the velocity in a moving frame of reference. So if we have a frame of reference that is convecting with the vortex, this would be the velocity relative to that frame. Now, subbing this back into the force expression, we get something that looks like this. And note here that I've moved the constant u infinity outside of this integral. Because it's constant, we can do that. And now what we have is an integral of omega over the volume Vm. Now this is, by definition, just the circulation inside of Vm. So let's call this, based on our original definition, gamma V. Since we're looking at a two-dimensional flow, this vector is simply normal to the plane. And based on Kelvin's circulation theorem, which we talked about at the very beginning of the video, this is going to be equal and opposite to the bound circulation around the airfoil. So we're going to have here, this first term is going to be equal to u infinity cross omega b. Now, many of you will probably recognize that we have already now recovered what we were aiming for. So we have this u infinity cross gamma b, which is going to give us a force that is perpendicular to the free stream velocity. So this will be a lift as we defined it at the beginning. And of course, we could move this density that I have on the left-hand side here, move it over, and we've recovered the Katajkowski lift theorem. So we have to deal with this second term. So let us quickly show that this term vanishes. And this is where that assumption that the starting vortex is axisymmetric comes in handy. So let me redraw that vortex as I drew it before. There, so I've drawn it as axisymmetric as I can. And of course, I'm taking these shades of red to represent different values of vorticity. So we haven't assumed, as is done in the typical derivations, that the vortex is a point vortex. It could occupy finite volume. I'm merely going to assume that it's axisymmetric in its vorticity distribution. So to show that this second integral vanishes, let us consider 2 points on opposite sides of the vortex center, so symmetric about it. And we'll assume we have omega 1 at one point, omega 2 at the other, and the velocity at that point in the moving frame of reference is u1 prime. And we have the velocity at both points being u1 and u2 prime. This is the velocity in the moving frame of reference. And by the axisymmetry assumption, we have omega 1 equals omega 2, and u1 prime equals negative u2 prime. And so the cross product of the velocity and the vorticity on opposite sides of the vortex are going to be equal and opposite, so their sum will sum to 0. And if we do this for all pairs of points around the circle, of course, this entire integral is going to vanish. So there we have it. I can write that this is 0, and we have at last the Kutta-Joukowsky lift theorem shown in vector form, which, if we're just looking at the lift, gives us back the expression as we wrote it at the beginning. Where in this form, the sign convention is that a clockwise circulation is positive, whereas in the vector form, the positive direction for gamma b is out of the page. You can use whichever sign convention you like, but this is the destination we are aiming for. So I will leave this video at that for today. If you have any comments, let me know below. Oh, and I should say one other thing. So we had made the assumption, in order to get here, that there is no vorticity or gradients of vorticity on the boundary SM here. So in a follow-up, what we could consider is what happens when that isn't true. So we could consider that we have, say, lower Reynolds number, and we do definitely have a viscous drag where we are generating some vorticity in a thin shear layer that connects the flow around the airfoil to the convecting starting vortex downstream. So of course, now that if we have vorticity crossing that boundary, we'd have to deal with it. And so this allows, in this framework, we could derive an expression that gives the Katajkowski lift superimposed onto another term, which gives us the viscous drag component. Now, this is something that's more difficult to do in a rigorous way in the classical derivations because, of course, we assume potential flow, where all of the vorticity field is represented by vortex singularities. So this framework is more general, will allow us to do more. But again, I will just leave it at that for today. So I'll snap forward and end the video on this frame here with our result. Thanks for watching.